So we've seen that before, and we've seen that we use the universal testing machine to do that. We've had a chance to work with that in the lab now. So we want to take a little closer look at what happens. We've seen so far the chalk. We didn't see it bulge very much because it wasn't much of a human observable shear, strain, but it definitely was straining, and eventually we saw the chalk flake off. So here's a more detailed vision, or a detailed cartoon of what our data actually looks like. Again, the vertical axis, the stress axis, is what we would consider a y and an x. And again, that's just mathematicians describing a graph. This is going to be the stress axis. This is going to be the strain axis. The strain axis is horizontal. The stress axis is vertical. And we saw before that this sort of has a linear data. The data sort of goes up and to the right and does so in a line. And eventually it stops following this line and starts to fall off, and then eventually it just snaps. That's when we saw in the lab when our material, our chalk, actually exploded or popped, or it wasn't very dramatic. It wasn't as if it was a large bang. There'll be other samples where there will be a large bang, but not this one. And we saw before that this particular linear region we called the elastic region, and this curved over region we called the plastic region. And again, in this cartoon, they're talking about the area underneath the curve. Of course, they're talking about energy capacity here. So this is the elastic region along the slope. Let me point it over here. This is the elastic region along the slope. This is the plastic region along the data. And if we look at the area under the curve, the energy capacity, we would definitely say this entire region was plastic, this entire region was elastic. So this is all review from before. And of course we saw failure as before. But what's happening here is we have a couple extra vocabulary words that we can use to get a sort of better color commentary of what's actually happening. We have this failure point, and of course this is the strain area, and when this sample breaks or eventually fails, if we come right back down and look to see where the strain ultimately, when the material broke, we can of course call that the ultimate strain, ultimate meaning the best or the highest that it went. So it sort of makes sense that if this is the failure point and the material isn't there anymore, we saw before some of these pieces of chalks just popped and split in half. When this does fail, that's the highest strain this material will get, so we call that the ultimate strain on this axis. And for the exact same reason, if we follow over here and look at the y-axis or the vertical axis, we get the ultimate stress. So we have the failure point, we have the ultimate stress, and we have the ultimate strain. And then you can see here there's sort of a transition area when the material stopped being elastic, which means it would stretch back if we let it alone, and it started being plastic, which means it started to move permanently. It started to get longer, and now that we've stretched it past this little point right here, it won't go back. So now we've made it longer permanently. And of course you can see right here this particular process of straining linearly and then stop following the elastic region, we call that the yield region, or in this case this is the yield point. And if you drive a car, we have yield signs, and when you're supposed to yield on your runway, it means you're supposed to give way and let everybody else go first because you are yielding. That's why we use the word yield here. What's happening is the material inside the sample within the elastic region is stretching, but it can come back. But when we get to the yield point, some of the material is literally driving past the other material, sort of back when we were talking about, let me go back one or two here, way back here with this guy, okay? So what's happening here is this shear, when we cut, the material on this side of the sample is permanently moving down while this material is permanently moving up. So we call that yielding. What's happening is one is moving relative to the other rather than both of them moving at the same time or in some sort of stretch mode. So as this material sort of walks up this elastic region, it would snap back if we allowed it to. It then eventually hits this yield point, just like this was a failure point and we talked about the ultimate stress, this is the yield point, so we can talk about the yield stress. And yeah, there's an appropriate yield strain, but typically we talk about the yield stress. So some additional vocabulary words that we didn't have before. We had the failure point, ultimate, both ultimate stress and ultimate strain, and yield, the yield point and the yield stress. So we continue to talk about the same ideas. We just happen to have more colorful language, or more synonyms and additional words to be able to describe what's going on. So calculations wise, can we get some actual numbers? Here's another picture of this. We have, in this case, here's the data running up here. Again, we have the vertical axis is stress, the horizontal axis is strain. And sometimes the sort of, just like sometimes we call a polymer material a plastic, sometimes we call the stress axis the strength axis, because we sort of talk about, wow, that really must be a, how strong are you, bro? Can you bench 300 pounds? Again, pounds. Stress would be pounds per unit area, but when we talk about lifting or benching a certain amount of force in pounds, we usually, as humans, consider that to be strength. So sometimes that vocabulary sort of shows up inside of our material science as well. So sometimes we'll talk about the stress, and we'll synonymously call it strength. So up here I have, this is most definitely the stress axis, but sometimes it's nicknamed the strength axis. Here's our data. Okay, it comes up here, and you'll notice that, oh, by the way, this particular sample sort of gave way a little bit, and we saw a lot of the chalks in lab. The chalk sort of followed a nice line, and then the chalk sort of broke a little bit, or it sort of gave way. So in this particular cartoon, we most definitely have a yield point right here, and then it stops following this linear thing, and it can have any kinds of shapes. This shape happens to come up, and then it happens to fall back down. It doesn't really matter whether it's increasing or decreasing. And then eventually it starts to fracture. So over here you'll notice this particular thing, it's also about necking and strain hardening. So what we're talking about, if we're talking about necking down, we must be talking about pooling or tension. So this isn't the chalk, this happens to be pooling something apart. So the material is going to pool apart, and it's going to do so linearly inside this area over here, this region of the graph, where we're going to get our elastic region. It's then going to go to the yield point, and of course we can call this the yield strength, come across to the stress axis, or nickname the strength axis and call it the yield strength. And then it continues to come up, but you'll notice that it is increasing as it's sort of changing in this yield region, okay? And they specifically call that strain hardening. What's happening is this, even though it's straining, different strands or different parts of the material are starting to push against each other, and it turns out that it actually sort of reinforces it. It reinforces the material, because the strands, or the strands inside the material, are sort of being slammed against each other. So this region where it continues to yield and not being linear, but continues to increase, we call that strain hardening. And then over here you'll notice that this thing is starting to fall back down. Even though we're pooling it and it's getting longer, it's getting weaker and weaker and weaker as we go. So what's happening is, if I was back to being gross and pulling my gum out of my mouth again, what's happening here is it literally is starting to neck down, and it's getting thinner. And as it gets thinner, it sort of loses the battle and it sort of falls off. So this is most definitely a necking region. And we have these three different lines. So where it started to transition from being elastic to plastic, we're going to call that the yield point. And then of course this is the yield strength. Way up here, this is the highest stress it ever got to. So we're back to ultimate again. Here we're going to talk about ultimate strength. That's the highest it ever went on the stress area. We're going to call it strength. And then over here, this is the fracture or the break. We're going to call this the breaking strength, or the fracture strength. Down here on this particular thing here, the slope, notice this slope is linear. We know how to calculate y equals mx plus b. We know how to calculate rise over run. And oh, by the way, we talked about different values before we get yet another. We talked about Poisson's ratio before, and now we're going to talk about this ratio of rise versus run, and this happens to be called Young's modulus. Modulus happens to be a very fancy word for slope. So this is Young's slope, or Young's modulus. It's the rise over the run for a stress versus strain material. So that we're going to look at this slope, and depending on what slope the sample has, that will tell us what the Young's modulus is as we calculate it, and it will allow us to tell which material is strong and which material is not strong.